Good morning, everybody, and welcome to the 13th episode of our AP Calculus Free Response Question Advent Calendar. It's December 13th. That means we're officially over the halfway point, because 13 days from now is December 26th. That's the day after Christmas. That's the day after our last episode. We're over halfway through. It's crazy. Today's a big day for my students, most of my students. Today's the day they're taking their midterm exams. And here I am, eating chocolate. But hey, I'm doing math too. Let's find the 13th compartment on our calendar. Ooh, there it is. Unlucky 13. Not great for the day of math midterms, but hey, what are you going to do? Let's zoom into this bad boy. 13. It is right there. Okay. So I'm going to get into this compartment with some chocolate. Maybe it's going to have that red lint truffle in it. And I will put today's AP Calculus free response question on screen now. This is today one of those questions that we're doing. It's got like a graph of a derivative, and these can be surprisingly time consuming. Like, this is probably going to take us a little while to work through. You got to do some geometry, which is fun. You really got to understand integrals and derivatives and inflection points and all that. It's a tricky little problem. So, as always, I encourage you to give it a try before we work through it. I'm making a mess of unwrapping this. Jeez-a-loo. I already feel like I have to brush my teeth just looking at this. Oh, it's very firm chocolate. Kind of getting sick of eating so much chocolate. I ate so many cookies the last few days. I need to oh God. Okay. Let's do some math. This is problem 5 from the 2010 AP Calc AB Exam. This was part of the no calculator section. We got a nice picture here. Let's take a look at what the question is. The function g is defined and differentiable on the closed interval from -7 to 5 and satisfies g of 0 equals 5. The graph of g prime of x, the derivative of g, consists of a semicircle and 3 line segments, as we can see here. So make sure you notice this is the graph of g prime, not the graph of g. Part A is to find g of 3 and g of -2. Let's start off with g of 3. This is pretty simple to find if you remember how integrals and derivatives work. We have a given value of g, which is g of 0. We know g of 0 is 5, so we can find g of 3 if we take 5 and then add the sum of the change of g from 0 to 3. By that, I mean we have to add the integral of g prime of x dx from 0, because it's at 0, that we know g is 5, and that's our only known value, so we have to start there. And then we accumulate these changes, these g primes, up to 3, the desired value. If this isn't clear at a glance, you might be more comfortable noticing that the integral of g prime of x from 0 to 3, just this part here, is clearly going to be g of 3. We're undoing the derivative because of the integral, and then plugging in the upper bound, so g of 3, minus g of 0, right? And then, well, g of 0 we know is 5, so if we have this addition of 5 on the left, that's going to cancel out with the g of 0, and all that's going to be left is g of 3. Clearly the equation is true then. G of 3 equals g of 3, exactly what we want. Now let's go ahead with evaluating this. We're going to have 5 plus this integral. Now to evaluate this integral, we can look at the given graph of the derivative. The integral of the derivative gives us the area under the derivative, so we can calculate this integral by calculating some areas. In particular, we need the area under the curve, the area under the derivative, from x equals 0 up to x equals 3, which is right there. So we need all of this shaded area. And we can see that this shaded area is made up of a quarter circle, half a semicircle, and this right triangle. The area of this quarter circle is 1/4 the area of the whole circle. The area of a whole circle is pi r squared, and r, the radius, in this case is 2. So this is going to be pi times 2 squared, or pi times 4, but we only want the area of a quarter of this circle, so we have to multiply it by 1/4. So that's this area here. Now we just need the area of this right triangle. That, of course, is 1/2 base times height. The base from here to here is just 1, and the height we see is 3, because that's the y-coordinate of that upper point. So the base of 1 and the height of 3. And then we just have to simplify this. 5 is the same as 10 halves. I'm writing it in terms of halves because here at the end we have 3 halves. So let's add 3 halves over there. And then the pi term will leave at the end. 1/4 pi times 4 is just a whole pi because the 4th and the 4 cancel out. Finally, 10 halves plus 3 halves is 13 halves, so our final answer is 13 halves plus pi. Again, we start at the known value. We know that g of 0 is 5, and then we have to accumulate g's changes by integrating its derivative from 0, where we started, to 3. If we do that, we get g of 3. It's 13 halves plus pi. We're not done with a yet, though, because we also have to find g of -2. We find g of -2 in the same way. Take the point we already know, 5, right? G of 0 is 5, and then we need to accumulate backwards to -2. So this is the integral from 0, where we are starting, to -2. We're adding up those rates of change, so we're integrating g prime of x with respect to x. This is just going to be 5, and then the integral of g prime, again, is the area under the curve. But because we're going backwards from 0 to -2, which I'll shade in blue, that's this area here, from 0 to x equals -2. Because we're going backwards, we're just going to have to hit this area with a negative sign. This area we can see is again just the area of the same sort of quarter circle. We already calculated that area as pi, so this is just negative pi. Again, it's negative because we're going backwards from 0 to -2. So this is going to be 5 plus negative pi. Basically, what's happening is that we're starting at g of 0, which we know to be 5, and then by integrating backwards, we're undoing the change that occurred from -2 to 0, and thus that gives us g of -2, which we find is just 5 minus pi. And now we can move on to part B. Find the x-coordinate of each point of inflection of the graph of y equals g of x on the interval from -7 to 5, and explain our reasoning. In order to find the points of inflection of g of x, we're going to have to look at the graph of the derivative. A point of inflection is where the derivative goes from increasing to decreasing, or decreasing to increasing. So, by looking at the graph, we can see that those occur at x equals 0, 2, and 3. At x equals 0, the derivative goes from increasing to decreasing. At x equals 2, the derivative goes from decreasing to increasing. And at x equals 3, the derivative goes from increasing to decreasing. If we look at another point like x equals -2, the derivative is increasing on both sides of -2. So that would not be a point of inflection, just for a counterexample. And there it is written out. Again, we find the points of inflection by looking at where the derivative switches from decreasing to increasing, or from increasing to decreasing. So those are our points of inflection at x equals 0, 2, and 3. Moving on then to part C. The function h is defined by h of x equals g of x minus a half x squared. We want to find the x-coordinate of each critical point of h, where x is between -7 and 5, and classify each critical point as the location of a relative minimum, relative maximum, or neither, and explain our reasoning. Let's begin by taking the derivative of h so that we can find the critical point. Since h of x equals g of x minus a half x squared, h prime, the derivative, is going to be g prime of x, and then apply the power rule for this part. That's going to be minus x. Okay, g prime of x minus x. Let's write that down here for part C. H prime of x is g prime of x minus x. Now, to find critical points, we need to see where this derivative either doesn't exist or where it's equal to 0. We're only interested in the interval between -7 and 5, and we were told that g is differentiable on that entire interval. And of course, there's no problem subtracting x on that interval either. So there's nowhere on the interval where the derivative doesn't exist. So the only critical points are going to be where this derivative is equal to 0. Now, if this equals 0, g prime of x minus x equals 0, then of course we have that g prime of x would equal x. So where does that occur? It may help to think about this geometrically. G prime of x equals x wherever the derivative, g prime, intersects the line y equals x. So let's come back to our graph of g prime and graph the line y equals x. The line y equals x passes through 0, 0, it passes through 1, 1, it passes through 3, 3, so the line should look something like this. The points we're looking for are where this derivative, the graph in black, intersects this line y equals x. That would be where g prime of x equals x. We can see clearly this occurs at the point 3, 3. That's a point where g prime of x equals x because they're both 3. And it also appears to occur at one point on this semicircle and nowhere else. Now, to figure out exactly where it occurs on this semicircle, it will help to write an equation for it. So you have to know how to write the equation of a circle centered at the origin with a radius of 2. The equation of a circle centered at the origin with radius 2 is right here. We're only interested in the semicircle that's above the x-axis. We can find that by just solving for y, and that's going to be the square root of 4 minus x squared. So the derivative, g prime of x, between x being -2 and 2, the derivative is this, the square root of 4 minus x squared. That's an equation for this semicircle here. Again, this is between x being -2 and +2. Now, with this equation, we can figure out at exactly what x-coordinate it intersects the line y equals x. So we'll just write x equals the square root of 4 minus x squared and solve this. To do that, we'll square both sides. So x squared equals 4 minus x squared. Add x squared to both sides. So 2x squared equals 4. Divide both sides by 2, so x squared equals 2. And then we find that x equals the square root of 2. It's not the case that x equals -√2, even though that would satisfy this equation. We can see just from our picture that the point we're looking for has a positive x-coordinate. Thus, where does g prime of x equal x? Where are these critical points? That would be at x equals 3, and as we just found, x equals √2. Now, we just have to classify these critical points. In order to classify the critical points, we need to think about the behavior of this derivative around these critical points. If the derivative switches from positive to negative, for example, that means that the function h switches from increasing to decreasing, and a point like that would be a maximum. So let's take a look back at our picture and focus on these critical points, x equals √2 and x equals 3. If we look at x equals √2, we can see that to the left of this, so over here, to the left of this, the derivative g prime is greater than x, right? It is the upper function. So if we were to look at g prime of x minus x, which is h prime, right? H prime is g prime minus x. Clearly, to the left of root 2, that's going to be positive because g prime, we see, is bigger than x. Okay, so it's positive there. Now, what about to the right? Well, to the right of root 2, x is above g prime. So to the right of root 2, it's negative, and it stays that way. Afterwards, we see that y equals x remains above g prime. So at root 2, the derivative h prime switches from positive, because this is bigger than this, to negative, because now this g prime is smaller than this. And here that reasoning is written out. We could clearly see that between 0 and root 2, g prime of x is greater than x, and thus h prime of x is positive. On the other hand, between root 2 and 5, we found that h prime of x is less than or equal to 0. It is non-positive because g prime of x was less than or equal to x. We see g prime is underneath y equals x. Okay, so at root 2, it switches from positive to non-positive. Thus, h has a relative maximum at x equals root 2. It's positive derivative, so it's increasing, and then it's either staying the same or decreasing based on our evidence. And neither a minimum nor maximum at x equals 3. That's because at x equals 3, that's in this interval, and we see that the derivative doesn't switch sign in that interval. Throughout that entire interval, which contains x equals 3, the derivative h prime is less than or equal to 0, so there's no switching of signs. In fact, the only time the derivative is 0 on this interval from root 2 to 5 is at that critical point, x equals 3. Everywhere else in this interval, h prime is negative, so certainly that would not be x equals 3, the location of a min or a max. And that completes our solution to free response question 5 from the 2010 AP Calc AB exam. Let me know in the comments if you have any questions, and be sure to check out the full AP Calculus free response question Advent Calendar playlist, link in the description and the pinned comment. We still have a whole lot of calculus to go. We're just over the halfway point, so be sure to subscribe and follow that playlist so you don't miss all the calculus to come. I'll see you tomorrow, and I hope you're having a great December. Thanks for watching.